Today we want to review for the test over Units 10 and 11. If you'll notice, there are quite a few definitions. Not only do you not want to forget to do those definitions, they are due on the day of the test, but I just want to emphasize that there are quite a few of these definitions on the test. This is a very definition-heavy, concept-heavy test. So make sure that you not only do these definitions, but that you study them. The test is going to be all Scantron, so it's all multiple choice. So that will help because you know that recall is a little more difficult than recognition. So you need to be able to recognize these definitions, and so that makes it a little bit easier. But if you don't study for these, you're not going to know the difference, for instance, between a Bronsted base and a Bronsted acid. You have to actually study those definitions, so please do that. As far as the to know part, make sure you know about the Henry's Law and the related principles of solubility. When we talk about gases in a liquid, remember that if you want to increase the solubility of a gas in a liquid, you want to decrease the temperature and you want to increase the pressure. Think of a carbonated beverage. In order to keep the fizz in that carbonated beverage, you want to keep it cold in the refrigerator, decrease the temperature, and you want to keep the lid on, so increase the pressure. So keep that in mind. When you're talking about a solid in a liquid, to increase solubility, about all you've got to work with on that is temperature, and remember, it's opposite of the gas liquid system. In a solid liquid system, you want to increase the temperature. For the vast majority of solid liquid solutions, increasing the temperature will increase the solubility. So keep that in mind. If I ask you a question about water, the answer is probably going to be hydrogen bonding. So keep in mind that you need to look at those notes. Go back to notes 10-1 and remind yourself about the different factors that are affected by hydrogen bonding, and make sure that you know those. As far as factors affecting the rate of solubility, remember that if you want to increase solubility, you're going to heat the solution, increase the rate of solubility. That's different from increasing solubility, increasing how fast something dissolves. Heat it, stir it, and decrease the surface area. Remember, depending on how it's stated, it may also say, oh, I said that wrong. Decrease particle size, increase the surface area. You want to crush it up, so you're decreasing the particle size, but you're increasing the surface area. So I just made my own point. Be careful about how it's being stated, because one way it could be stated, the correct answer is decreasing when it comes to particle size. The other way, when it comes to surface area, it's increasing. So watch that. Examples of solution suspensions and colloids. There's a whole table on 10-2. Really, seriously, if you know the definitions of solutions and suspensions and colloids, go back over that information. If you know those definitions, then you should be able to come up with whether something's a solution, a suspension, or a colloid. There's a table on 10-2 that has a lot of those examples, so make sure you go over that. As far as examples of indicators, the main two that I'm worried about are litmus and phenolphthalein. Litmus, if you're talking about an acid versus a base, an acid for litmus turns blue litmus to red. It turns red litmus to blue if it's a base. Now, as far as phenolphthalein is concerned, in acidic solution, phenolphthalein is clear, and in basic solution, phenolphthalein is like a magenta, hot pink, purple color. So make sure you know those color changes. If you don't go back and review some of these things that I tell you to review, you're going to miss some of those questions. So treat those notes, going through those, like your review, and make sure you know examples of those solution suspensions and colloids, and make sure you know about how hydrogen bonding affects those. I'm not going over it here in the review. You can read that in those notes, but just make sure you do that. Okay, reviewing molarity problems. Remember that molarity can be written as molarity equals moles over liters, depending on how the question is asked, or it can be written as molarity equals mass over molar mass, which is moles over liters. So depending on what it's asking for and what information it gives you, it's going to determine which one of those is going to be used. Now in this case, it asks you to find the molarity of the solution, and it gives you the volume of the solution, and it gives you grams of the solute. So you're going to want to use the mass over molar mass form of the equation. It is solving for molarity, so we're going to plug those values in. Molarity is going to be equal to the mass, which it gave us as 7.55 grams of the potassium permanganate. Now we're going to then divide that by the molar mass of potassium permanganate. If you add up 1 potassium, 1 manganese, and 4 oxygens, you're going to get 158.04 grams per mole. And remember, when you're putting in the volume, it has to be in liters. Rule of 3, move that decimal over 3 places to the left excuse me, 3 places to the left to get from milliliters to liters. So 0.275 liters for your volume for this. And when you work this out, the molarity comes out to be 3 sig figs, 1.74 times 10 to the negative first molar KMnO4. So that's the answer for that one. For the next problem, this time it's asking us to find grams of the sodium sulfate. So that should automatically tell you what equation that we need to use. And it gives us information on the volume of the solution and on the molarity of the solution that we're looking at. So since it's grams, hopefully you determined that we were going to use the mass over molar mass form of the equation. This time we're going to be solving for mass. So solving for mass, remember, we want to multiply both sides by liters, which is going to cancel it or reduce to 1 on this side. We also want to multiply both sides by the molar mass, which is going to reduce it to 1 or cancel it on this side. So we end up with the fact that the mass is equal to the molar mass times the liters times the molarity of the solution. The molar mass of sodium sulfate, if you add up 2 sodiums, 1 sulfur, and 4 oxygens, you end up with 142.05 grams per mole. We have a volume value of 500 milliliters, but keep in mind that we need that in liters. Rule of 3, moving the decimal 3 places to the left, we get 0.5 liters. And finally, the molarity is 0.1 moles per liter. Molarity is always easier to put into problems as moles per liter because it shows the cancellation better. And when we cancel our units, notice what happens. We get moles canceling, we get liters canceling, and we're left with grams. Our answer then, notice that it's going to be 1 sig fig because of both the 500 milliliters and the 0.1 molar from the original values. We end up with 7 grams of sodium sulfate. So that's our quick review of our molarity problems. As far as naming and writing formulas, remember that if it is a binary acid, just 2 elements, no oxygen, starts with an H, it's going to start with hydro. So pause it real quick and point out and find your binary acids. Hopefully you picked out hydrofluoric acid and hydrosulfuric acid. Remember, if it's a binary acid, it starts with hydro. The next thing that I would do would be to pick out any exceptions to the rule where your acids are concerned. Remember, our exceptions to the rule are the phosphorus and sulfur oxyacids, and our acetic acid, or Chaku acid. So here's one of our exceptions to the rule. CH3COOH is acetic acid. H2SO3 is sulfurous acid. And the 2 ones that I want you to know for sure of the exceptions to the rule for the test are H2SO4, which is sulfuric acid, and H3PO4, which is phosphoric acid. So make sure you know those 2 exceptions to the rule along with our acetic acid. Know those. Now the rest of our oxyacids you can get simply by counting oxygens and remembering the rule. If you have 1 oxygen in an oxyacid, and the example of that one is right here with 1 oxygen, starts with an H. Remember those start with hypo, so there's going to be hypo for a prefix. Then the root, chlor in this case, and it always ends in us when there's 1 oxygen. So hypo, root, us, hypochlorous acid. If it has 2 oxygens, and the example of that would be over here, we drop the prefix and simply write the root, which is chlor again, and it still ends in us, so chlorous acid. If it has 3 oxygens, example here, then we change the ending to ic, so iodic acid. And if it has 4 oxygens, as this one does, then we pick up another prefix, per in this case, with the root, brom, and still ic on the end. So us, ic for the endings. If there's 1 oxygen, it's hypo, then there's no prefixes on 2 or 3, per on 4. So know how to do your rules for those oxyacids. Now when it comes to writing formulas for our bases, those are easy. All we have to worry about for our bases is whether it needs a Roman numeral or not. Barium is in group 2A. If it's in group 2A, one of our known charges, we don't need a Roman numeral. It's just barium hydroxide. If, on the other hand, it's something like iron, iron is in one of our question mark positive areas of the periodic table. We do not know the charge. It must have a Roman numeral. And remember, all we have to do, since hydroxide is negative, is to look at that end number, and it will tell us what our charge is. So iron is going to be iron 3 hydroxide. And as far as writing formulas for them, remember ammonia is the base that I expect you to know, NH3. copper 2 hydroxide. If you know what the charge is on copper, it makes it really easy because all we have to do is look at the Roman numeral and it will tell us how many hydroxides we need to put. And the last one is not periodic acid, as people keep wanting to call it. It's periodic acid, which should tell you that there's 4 oxygens. It's going to start with an H. Since it's iode for the root, it's iodine. And then, since it starts with per and ends with ic, we know it has 4 oxygens. So periodic acid, HiO4. Now, as far as listing the strong acids, you have to recognize them. You don't have to, I'm not going to make you list them and recall them, but you do have to recognize them. Hydrochloric acid, hydrobromic acid, hydroiodic acid, HNO3, nitric acid, sulfuric acid, perchloric acid, permanganic acid, and chromic acid. Should be 8 strong acids, and those are the ones that you have to be able to recognize to know if they're strong or not. As far as the strong bases, remember the rule is the strong bases are hydroxides of groups 1A and 2A, except for, and hopefully remembered, magnesium. Magnesium hydroxide is insoluble, therefore it doesn't produce virtually any hydroxides. Maybe a few, but not much. So there's your rule for the strong bases. And that information we need to know in order to be able to show ionization reactions, because remember, it's determined what kind of arrow we use by whether it's a strong or a weak acid or base. Since HClO3 is not on the strong list, it's going to get a weak arrow. Now remember, we put aqueous after everything. I may not do that necessarily on the test. Sometimes I leave off some of those things because there are it just takes so long to type it up, but it's all multiple choice, so you'll get to choose it that way. So HClO3 aqueous is going to react to form H plus aqueous. Remember, the only thing that splits off the acid is the hydrogen. Everything else stays together with a negative sign, so make sure you're paying attention to that. A lot of people keep trying to split the chlorine and the oxygen away from each other. HI aqueous, I'm sorry, I just told you that this was determined, that we determined strength by what kind of arrow, and then I just went ahead and wrote up the wrong kind of arrow. Since HClO3 is a weak acid, it's not on the list. It's going to get a weak arrow, that double arrow. HI, on the other hand, is on the list, and therefore it's going to get the strong arrow, the single arrow to the right, a completion arrow, and we get this for our ionization. NaOH is a base, and sodium is in group 1A, so it's going to be a strong base. So we get a strong arrow. I'll get it right this time. Strong arrow, and we end up with Na plus aqueous and OH minus. The hydroxide splits off. NH3, you have to know, it's the one exception, and it is on the test. So if you don't recognize it as being the only one that I'm requiring you to show reacting with the water, so we can see water's role, then you're going to not be able to recognize that. It is weak, so it's going to get the double arrows, and we'll end up with NH3 being a dirty, nasty hydrogen-stealing base. So NH4 plus and OH minus are what we're going to form. Those, sometimes we can put aqueous on them or not, but it shows the role of water, so I tend not to on those. Finally, HiO3 is a weak acid, so therefore it's going to get a weak set of arrows. equilibrium arrows, if you will, but showing that not all of this is going to ionize. We get H plus, aqueous, and IO3 minus. Now I do want to show you one more because there's going to be one like it on the test, and that's for something like, let's say calcium hydroxide. If we have calcium hydroxide, it is a base. It is a strong base. It is calcium's in group 2A, so it's going to be strong, so it's going to be a single arrow. And remember what this is going to look like. We're going to get something other than a positive charge for calcium because it's got 2 hydroxides with it. That means calcium's charge is going to be a 2 plus. And when we write the fact that there are 2 hydroxides, please don't forget that it's going to come out, and that 2 is going to come out in front. So this is what it's going to look like if we have a base with more than 1 hydroxide. So moving on, finding pH. Remember, when we find pH, we can go directly to the hydrogen ion, from the hydrogen ion concentration. The pH is going to be 3. And since the pH is 3, we know that it's less than 7, so it's going to be acidic. If we're, again, trying to find the pH every time, we cannot get it directly from the hydroxide ion concentration. We're going to need to find pOH first. So pOH is going to be 5. And remember, if we know the pOH, we can simply subtract that from 14, and we can get that the hydrogen, or the pH is 9. And once I know that the pH is 9 greater than 7, it's going to be basic. The pOH, if it's 11, again, we can subtract that from 14 and get that the pH, once again, is 3. So if the pH is 3, it's going to be acidic again. And finally, if the H plus is 1 times 10 to the minus 7 molar, then we know that the pH is 7, and if the pH is 7, at least at 25 degrees Celsius, we've got a neutral solution. So that's the pH and pOH. It's going to be in a table form, kind of like that one worksheet that you did when you see it on the test. I've got it figured out a way to do it so that you can fill in the table and answer it still on multiple choice. So you might want to glance at that table again and make sure you remember how that should look. Okay, as far as the reactions, make sure that you remember to circle out your hydrogen and hydroxide and make sure those are equal, because that tells you how many waters you have. And then use the rest of it, metals first, to form the salt, IO4. So there's the first reaction. It was already balanced. The second reaction, we've got 2 hydrogens and only 1 hydroxide, which is going to tell us that we need a 2 in front of the hydroxides. And that tells us we need 2 water molecules. It also is going to let us come up fairly quickly with the formula for the salt. Metal first. The balanced equation says there's 2 lithiums in it, and SO4 for the rest of it. Now, that makes, we could find it just as easily if we found that lithium had a +1 charge and sulfate had a -2, but this simply is a quicker way to find that out. The next one, 3 H's, 1 OH. That means we're going to need 3 in front of the KOH to get our base, our hydroxides balanced, which tells us we have 3 water molecules, and tells us what our formula should be. K3 for the salt this time, and 1 PO3, potassium phosphite. And finally, the last one, circle the hydroxides. There are 3 of them. Circle the hydrogens. There are 2. In order to balance this, we're going to need to put a 2 in front of the aluminum hydroxide and a 3 in front of the hydrosulfuric acid, which gives us 6 hydroxides and 6 hydrogens, which tells us we have 6 water molecules, and that the formula of the salt should be Al2 S3 for the formula of that salt. Finally, the titration problem. Remember, in the titration problem, we must have a balanced equation. Barium hydroxide is BaOH2, and it's reacting with phosphoric acid, H3PO4. That's going to react to form, if you look at what we've got, two hydroxides and 3 hydrogens. We're going to need a 2 in front of the phosphoric acid and a 3 in front of the barium hydroxide. And we're going to get the salt of Ba3PO4 out of it, and the fact that there's 6 water molecules. So there's our balanced chemical equation. Filling in our values, remember our rules. All of these milliliter values need to be in liters in order for it to be easier to solve. So I'm going to put 0.022 liters over barium hydroxide and 0.035 liters over the phosphoric acid. It tells us that we have a 2.0 molar solution. Remember, we always want to label it as moles per liter when it's molarity, and we're trying to find moles per liter for the phosphoric acid. Now, as far as the value that we're going to start with, we're always going to start with the simplest known value. We cannot start with an unknown value, a value that it pertains to the unknown. So we can't start with 0.035 liters, and we cannot start with a complex unit, so we're not going to start with the 2.0 moles per liter. So it looks like we're starting with the 0.022 liters of barium hydroxide. And the value that we're going to use with that, we need liters on the bottom, so it looks like an understood 1 liter of barium hydroxide for every 2.0 moles of barium hydroxide. And now we can use our balanced chemical equation to come up with a mole ratio. So our mole ratio is going to be 3 barium hydroxide moles for every 2 moles of phosphoric acid. The barium hydroxide needs to go on the bottom to cancel. So 3 moles of barium hydroxide for every 2 moles of phosphoric acid. And so far we've canceled liters, we've canceled moles of barium hydroxide, we're at moles of H3PO4 now, and we're wanting molarity. So be careful. We don't want moles to cancel. We want to be left with moles on top. We want liters on the bottom, and the only liter value we have is 0.035 liters for our phosphoric acid. So that's going to leave us with liters. Oh, I'm sorry, I wrote that wrong. Don't put that. Remember, we don't want any other units on top. We want moles per liter. That top value is going to be simply 1. Please do not make that mistake whenever you're taking this test. When you multiply and divide out this, then you're going to end up with, to 2 sig figs, 0.84 molar H3PO4. Now make sure and go back to your worksheet over titration and make sure you study the other type of problem that ends up solving for milliliters. Make sure you can do both of those types of problems. I didn't put them both on the review, but make sure you can do them both.